This module discusses how and why fluxes between the ocean and atmosphere are important for convection. We also must consider surface fluxes when evaluating the potential for convective growth. Where a flux of energy from the ocean to the atmosphere is low, deep convection tends to not occur. There are two types of surface fluxes we will discuss: latent heat fluxes and sensible heat fluxes. The latent heat flux is that between the atmosphere and surface associated with the phase change of water. Evaporating ocean water into the atmosphere is one example of a positive flux of latent heat to the atmosphere. Eventually, the evaporated water will condense back into liquid water, and when it does, it will cause warming as water transitions into a lower energy state. The sensible heat flux is a conductive flux between the surface and the atmosphere. A warmer surface translates to a higher sensible heat flux. One way of defining the two terms is shown here. It is known as the bulk expression of the fluxes, which contrasts with a different method called the eddy covariance method, which we'll see a little bit about later. Note a couple things. First, both fluxes are proportional to the near surface wind speed, u. This means that fluxes go to zero where there is no wind near the surface, at least approximately so. Second, the heat fluxes are proportional to the difference between properties of the sea surface, denoted by the subscript S, and the properties of the atmospheric layer just above the ocean surface, often known as the surface layer. Q sub S is computed as the saturation-specific humidity that air would have if it were the same temperature as the ocean's surface. The C variables, C sub Q and C sub H, are known as bulk transfer or exchange coefficients, estimates for which are beyond the scope of this course. The previous formulation indicates that fluxes vary linearly with wind speed u. However, reality is a bit more complicated. As wind speed increases, surface roughness also increases, and this causes a change in the exchange coefficient. As seen in this plot, latent heat fluxes, estimated from ship data, increase non-linearly as wind speed increases. However, the same general concept of fluxes increasing with increased wind speed generally holds true. Consider some typical profiles of variables in a convective boundary layer. A few different layers within the atmospheric boundary layer are denoted in this figure. The surface layer is the thin layer closest to the ocean surface. The mixed layer makes up most of the boundary layer, and then above that is an entrainment zone in which free tropospheric air is mixed with the boundary layer air. A few different variables are plotted here as profiles in the boundary layer. You can see that almost each is relatively constant in the mixed layer. The first plotted is virtual potential temperature, which is a function of potential temperature and water vapor mixing ratio, as we'll see on the next slide. Specific humidity tends to slowly decrease through the mixed layer, while wind speed increases from zero right near the surface to something larger than that, which is relatively constant on average throughout the mixed layer. The variable of interest that we will focus on next is the buoyancy flux, this W prime theta V prime term. It is proportional to the eddy covariance of vertical velocity and virtual potential temperature, and it decays with height quickly in the mixed layer, as we can see in this plot. A positive buoyancy flux in the surface layer means that the ocean is transferring energy to the surface layer, such that it supports the upward acceleration of thermals that develop in the mixed layer and rise to become cloudy updrafts. A detailed explanation of the eddy covariance flux method for estimating fluxes will not be covered here, but can be found in a course on boundary layer meteorology or air-sea interaction. We will look a little more into the buoyancy flux, however. Because it is related to vertical kinematic flux of theta V, and theta V incorporates both moisture and temperature, the buoyancy flux is related to fluxes of latent and sensible heat. The eddy covariance expressions of turbulent, latent, and sensible heat fluxes are shown here. Exchange coefficients, wind, and the difference between ocean and atmospheric properties have been folded into the terms W prime, QV prime, or W prime, theta prime. Some algebra can lead you to re-expressing the buoyancy flux in terms of the latent and sensible heat fluxes. And what you get is down here at the bottom. Note that for typical sea surface temperatures of around 300 Kelvin, this coefficient 0.61 times Cp times T over LV is about 0.08. This has important implications for the relative importance of latent and sensible heat flux on buoyancy of rising thermals in the boundary layer through the buoyancy flux. For a typical value of Q prime of order 0.1 and theta prime of order 1, the latent heat flux is roughly 1 to 2 orders of magnitude larger than the sensible heat flux. However, the contribution of the latent heat flux to the buoyancy flux is similar as that of the sensible heat flux. In other words, even though latent heat flux often dominates the sensible heat flux in magnitude, they are often similarly important for supporting buoyant updrafts that develop in the boundary layer. Let's consider a very simple example. The blue line represents the ocean surface. The boundary layer above it is well mixed, has a temperature of 28 degrees C, and a specific humidity of 18 grams per kilogram in this example. Let's consider two different cases with this setup. One in which near surface wind is 5 meters per second, and the sea surface temperature, or SST, is 25 degrees C. And another in which near surface wind is only 2 meters per second, but the SST is 30 degrees C. In which case is the flux from the ocean to the atmosphere larger? Pause here for a moment and see if you can figure out the answer. The case with the warmer ocean has the larger flux of heat to the boundary layer, despite its lower wind speed. This is because the 30 degrees C ocean is warmer than the 28 degrees C boundary layer. In the case of the 25 degrees C ocean, the atmosphere would actually flux sensible heat to the ocean. Based on the relationship between the buoyancy flux and heat fluxes, this means that a cool SST indirectly inhibits the upward acceleration of convection that's rooted in the boundary layer. It does so by reducing the convective instability of the environment by making the boundary layer cooler. Next, let's consider a different set of scenarios. On the right, we still have the 30 degrees C SST with 2 meter per second wind, but on the left is the 30 degree SST with a 5 meter per second wind. In which of these is the heat flux largest? Pause for a moment again to answer before moving on. You hopefully figured out quickly that given the same SST, the scenario in which the near surface wind is higher will experience the greater flux of energy from the ocean to the atmosphere. In other words, all else being equal, a strong, steady boundary layer wind can support growth of convection through enhancing surface fluxes. This is generally true for typical wind speed observed over tropical oceans, although the effect of wind on fluxes becomes more complicated at high wind speeds, such as those observed in tropical cyclones. The importance of surface fluxes on precipitation is readily seen in any map of climatological annual mean rainfall on Earth. Seen here is a map of annual mean SST. You should be highly familiar with maps like this by the time this course is over. The highest SSTs in the world are typically found over the Indo-Pacific warm pool. Warm SSTs extend in a narrow band north of the equator across the Pacific, and very warm SSTs are locally found near Central America, the Caribbean Sea, and in the summer over the Gulf of Mexico and tropical Atlantic. Relatively cool SSTs at low latitudes are often found off the west coasts of continents, where cold upper ocean currents advect water from higher latitudes toward the equator. A map of climatological mean precipitation rate is shown here. The pink, purple, red, black colors indicate where the most rainfall typically occurs. In the tropics, this corresponds closely to regions where SST was highest. The Intertropical Convergence Zone and the South Pacific Convergence Zone are particularly visible here as well. A bullseye of rainfall over the interior Amazon is also visible to the east of the Andes. Mid-latitude storm tracks are also visible, as well as the influence of terrain, such as near the coast of southeastern Alaska or the west side of New Zealand. Note also the lack of rainfall in regions of the tropics where SST is low, such as off the west coast of equatorial South America or Africa. In such places where surface water is fairly cold, convection is generally not sufficiently buoyant to reach far upward into the troposphere. Therefore, clouds cannot transport moisture far into the free troposphere, meaning the environment is dry above the boundary layer. Furthermore, as will be discussed in a different module, free tropospheric air tends to subside where moist convection is not active in the tropics. This increases static stability of the environment above the boundary layer, further decreasing the likelihood that long-lived deep convection can develop where SST is low.